Hello students, welcome to the class of Circuit Theory and Network. I'm Priyanjali Mukherjee, Assistant Professor of Electrical Engineering Department, Narula Institute of Technology. Today, in this class, we'll discuss on the DC transients. We'll discuss on the transient, the ideal inductor versus the practical inductor, transient response of RL circuit with DC excitation, transient response of RC circuit with DC excitation, transient response of RLC circuit with DC excitation, the examples. So, what is a transient? Now, if the circuit consists the R, L and C, that is the resistor, inductor and capacitor, and supply voltage is connected across it, then the current will flow through the circuit in some equations. Now, due to sudden change or application of voltage and current, the response of the circuit will change from the previous one, and that is known as the transient condition. Now, we have considered till now that DC resistive network in which the voltage and current were independent on time, because the relation was V is equal to I into R. Now, two passive elements, that is inductor and the capacitor, are introduced in the DC network, and the voltage and current relationship for these two elements will be like this: VL, that is the drop across the inductor, that is equal to L di dt, and across the capacitor it becomes 1 by C integration I dt plus Vc. This is at the 0 t 0 condition. Now, we can apply KCL, KVL, mesh analysis, current analysis, voltage, node voltage, all the methods and all network theorems, but the result in differential equations rather than the algebraic equation we have considered in the resistive network. Now, the transient current or voltage, that means that is a very quickly changing, which will occur always for a short period of time after the switching moments, and after the transient has ended, the current and voltage returns to a steady state condition. Now, from this graph we can see after the switching or after the application or changing in the voltage or current, the response is very much changing up to this region, and this region is known as the transient response, and after this the response becomes stable, and it is known as the steady state response. Now, the overall response is two types: one is transient response and another is steady state response, and summation of these two gives us the overall response. And the time taken for the circuit to change from the transient response to steady state response is known as the transient time. So, now consider the practical inductor and the ideal inductor. So, this one is the ideal inductor. So, in ideal inductor, we are considering that Vs is the constant voltage source and E is equal to 0, the switch is closed. And we are assuming that the initial current through the conductor is 0. So, hence I0 is equal to 0. Now, in an ideal conductor, we know V is equal to L into di dt. Now, the current through a linear inductor must be continuous, and the voltage across the inductor is not proportional to the current flowing through it, but the rate of change of the current with respect to time. Now, when the current is constant, the VL becomes 0, or Vs becomes 0. VL is the drop across the inductor, and the drop across the inductor, it is 0. So, under the steady state condition and the DC current, inductor acts as a short circuit. So, here the relation of I becomes integration of Ps by L dt, because the term I0 becomes 0, as it is equal to Vs by L into T, because after this integration it becomes Vs by T. Now consider the practical inductor, and in practical inductor there are some resistance of the inductor coil has to be considered, and the total resistance of the circuit becomes R1 plus RL. And if we consider R1 plus RL is equal to R, then we can find out the equation Vs minus R into IT minus L di dt equal to 0, or Vs by L, dividing both sides by this L, equal to R by L into IT plus L di dt. So we can compare it with the equation K equal to Px plus Dx dt, and general solution of this equation is given as e to the power minus Pt 0 to t K e to the power Pt dt plus C into e to the power minus Pt. So comparing this equation with equation 5, we can find out the current equation, that is e to the power minus R by L into T integration 0 to T Vs by L into e to the power R by Lt plus C into e to the power minus R by L into T. So this is the RL circuit with DC excitation is given here, and voltage source is constant, which is closed at T is equal to 0. So if we apply KVL in the circuit, then we are getting that V minus RIT minus L di dt equal to 0, or divide both sides by L, we are getting V by L equal to R by L IT plus L di dt. So as we know that the general solution of this type of equation is e to the power minus Pt into integration of 0 to T K e to the power Pt dt plus constant into e to the power minus Pt. So we can compare this equation with the equation number 9, and we can find out that the solution IT is given as e to the power minus R by Lt integration 0 to T V by L e to the power R by L into T plus constant into e to the power minus R by L into T. Now, the I becomes V by R plus C into e to the power minus R by L into T. Now, just before the switching, the inductor current is equal to 0. And the inductor, according to inductor property, it does not allow the sudden change in the current, so that at T is equal to 0, the IT is also 0. So from this equation, we can say this IT becomes 0, that is equal to V by R C to the power minus R by L into T. Or equating this, we can find out the value of this constant, that is equal to minus V by R. So we can put this value of C into the equation 8, that is IT is equal to V by R minus V by R e to the power minus R by L into T, or V by R into 1 minus e to the power minus R by L into T. Now this V by R is the steady part, and this V by R e to the power minus R by L into T, that is the transient part. So the overall equation is 1 minus exponential, so it becomes an exponentially increasing function, and this is the current profile. So if we plot the value of current with respect to T, then we can see that it will increasing exponentially, and after certain time it will go to a steady state value, that is equal to V divided by R. Now, if we consider the final value is V divided by R, then we need to find out what is the time constant. So the equation is e to the power minus V into 1 by V by R into 1 minus e to the power minus R by L into T. Now, if we consider that T is equal to L by R, then the equation becomes V by R into 1 minus e to the power minus 1, and which is equal to 0.632 into V divided by R, and V divided by R, that means the I steady, that is the current at steady state. So this T is equal to L by R time is required to reach the 63.2, because if we multiply it by 100, then it becomes 63.2. So the time required to reach the 63.2% of the steady state value is known as the time constant. and the ratio of 1 by tau is known as the damping ratio, and that is equal to R by L. So next we need to find out the voltage across the resistor. That becomes VR, that is equal to I into R. So putting the values, we can find out 1 minus e to the power minus R by L into T. So it is also in exponentially increasing function, and after some time it will go to its final value, and it will same at steady state. Its value will be the total applied voltage here. Now the voltage across the inductors, that is equal to VL, and that is equal to L di dt. So if we put the value of I in this equation, then we can find out that is equal to V into e to the power minus R by L into T, which is actually a exponentially decaying function. So from the final value V, it starts to decay. So the VL curve goes like this way. So this curve represents the VR versus VL profile. And next one is the RL discharging circuit. So in the previous case, we have considered that switch is connected to A and voltage supply is applied to the R and L in series connection. Now, in this circuit, we are considering that the circuit reaches the steady state, and after reaching the steady state, suddenly the voltage is withdrawn by opening the switch and throwing it to the B. So from this equation, now consider this loop, and here there is no voltage. So we can write down the KVL equation like this: 0 equal to RIT plus LDIDT. Now this type of homogeneous equation, the solution of this equation becomes C into e to the power minus q by t into t, which gives IT equal to C dash into e to the power minus R by L into T. Now, at t is equal to 0 plus, the inductor will keep the steady state current even the switch is in position B, because the inductor acts as a short circuit. So, we are putting the value, that is C dash into e to the power minus R by L into 0, because T becomes 0, that is equal to V by R, or we can find out the value of C is equal to V divided by R. So if we put the value C equal to V divided by R, then we can find out the equation of IT like this: V by R is equal to minus R by A into T, which is actually decaying signal. So this is the current profile of the discharging circuit. Next, we need to consider the transient response of RC circuit. So here the resistor and capacitor is connected in switch, and switch is closed at t is equal to 0 position, and supply voltage V is connected across this RC circuit. Now the total voltage V equal to R into I plus 1 by C I dt, or we can say I by C. If we differentiate both sides, then becomes I by C plus R into di dt is equal to 0. Again, we are considering the general solution of this homogeneous equations is equal to e to the power C into e to the power minus q by into t, and comparing this equation with this current equation, we can say that I equal to C into e to the power minus 1 by R C into t. Then the switch is closed at t is equal to 0, and the capacitor doesn't allow the sudden changes in the voltage. So it acts as a short circuit, and t is equal to 0 plus V equal to I equal to V divided by R, and I becomes then V by R into e to the power minus 1 by R C into T. So it is exponentially decaying function, and the capacitor is getting charged, and charging current actually dies out. And the voltage drop across the resistor becomes V into R, that is I into R, that is also an exponentially decaying function, and the drop across the capacitor, that is 1 by C integration of IT dt. If we put the values, then becomes V into 1 minus e to the power minus T by RC, which is exponentially rising function. So in this graph, we can see that the VC, that is the drop across capacitor, will start from 0, and then it goes to the final value at the steady state value, and the drop across the resistor starts to decrease like exponentially, and the time constant in this case becomes RC. So in the RC series circuit, the time constant is RC. Now the switch has considered in position 1 and it reaches to the steady state, and after steady state reaches, the switch goes to the position 2 in the same way, and the voltage source has been withdrawn. So if we apply KVL in this circuit, then we can see that 0 equal to RIT plus 1 by C IT dt. Now if we differentiate both sides, then equation becomes I by C plus R dt equal to 0. Now the general solution of this equation is same as C into e to the power minus q by into t, and according to that, the current is becomes C into e to the power minus 1 by RC into t. Now the t is equal to 0 plus, the voltage across the capacitor will start discharging current through the R in the opposite direction of the I discharging. Actual current was in this direction, clockwise direction I, but now the discharging current will start to flow in the opposite direction of the I, that is in the anti-clockwise direction. So I0 is equal to minus V divided by R, and if we put that, so I becomes minus V by R e to the power minus 1 by RC into T. So the voltage across the resistor VR, that is minus V e to the power minus T divided by RC. That means it is a this type of current decay in transient response, and the voltage across the capacitor Vc becomes V into e to the power minus T divided by RC. So this becomes the capacitor voltage across capacitor, and this becomes the voltage across the resistor. Next, both the inductor and capacitor are connected across the series with this resistance, and whole are connected to the supply voltage, and T is again closed at T equal to 0. The switch is closed. So if we apply the KVL, then the equation becomes T equal to RIT plus LdIdt plus 1 by C IDT. Now differentiating both sides, we get the RdIdt plus L d square IDT square plus I by C is equal to 0. So the characteristic equation can be written as T square plus R by L into P plus 1 by LC, where P is the ddt, that means the time derivative. So if we consider this characteristic equation, then by putting this Sridharacharyya's formula, we can find out the root, that is minus b plus minus root over b square minus 4ac by 2a, that becomes r minus r by 12 plus minus root over r by 12 square minus 1 by lc. Now we are considering that the P1 is alpha plus beta and P2 is equal to alpha minus beta, whereas alpha is the damping factor, and the total current is the summation of the steady state and the transient. That means it gives two equations, P1 e to the power P1t plus P2 e to the power P2t. Now the steady state equation gives from the particular integral, and the transient response is obtained from the complementary function. So there are three cases may be possible from this equation. First, consider r by 12 whole square is much greater than 1 by LC. So in this case, the root P1 and P2 becomes alpha plus beta and alpha minus beta, where beta is positive real. That means the poles are the real and unequal. So the I becomes e to the power at into C1 e to the power bt plus C2 into e to the power minus bt, and the current response is the overdamped. So in this case, the overdamped response is this one. And next we are considering r by 12 whole square is less than 1 by LC, and that means the poles are a plus j beta into a minus j beta, and beta is the imaginary poles. That means P1 and P2 actually are complex conjugate poles. So we are putting the values, and that is equal to the power 80 into C1 to the power jbt, C2 to the power minus jbt. That can be written as in form of cos beta t plus C2 into sin beta t. So the current response is undamped or underdamped or the oscillatory. That means this one. So it becomes underdamped and it becomes also oscillatory. And finally, when RL is by 2L whole square equal to 1 by LC, that means the poles are real and equal, then beta part becomes 0, and the current response is C1 e to the power alpha t plus C2 into e to the power alpha t. The response is critically damped. So this is the overall current response for all the cases. There is overdamped, underdamped, and the critically damped. So according to the Okay, varies of cases. First, we need to find out the pole locations, and according to that, the response will be varied in case of this RLC series circuit. So let us take another example. Uh, the time by a capacitor of 1 microfarad in series with 1 megaohm resistance is to be charged up to 80% of its final value. So we need to find out the time. The time constant is given as RC. So multiplying this capacitor value C, 1 microfarad into 1 megaohm by the value of R, it gives the 1 second. Now the from equation we can find out the for charging of capacitor Q equal to capital Q into 1 minus e to the power 1 by RC into T, and it is 80% of its value, so it becomes 0.8 capital Q equal to small q. Or we can compare this equation with this. So we give the equation, get the equation 0.8 equal to 1 minus e to the power minus t, which gives the value t is equal to 1.6 seconds. And in another example, consider find the current in a series having R equal to 2 ohm and L is given 10 Henry. When the DC voltage 100 volt is applied, need to find out the current after 5 seconds of switching on. Now, for the RL series circuit, the time constant is L by R, so it becomes 5 seconds, and I equation of I equal to I into 1 minus e to the power minus t divided by 5, and I is known as the steady state current. Steady state current means V divided by R. V is given as 100 voltage and R is 2 ohm, so V by R equal to 50 ampere. So we are putting the value of steady state current here, so I becomes 50 into 1 minus e to the power minus t by 5. And I transient is 15 to the power minus t by 5, and the steady state current is only 50 ampere. And after 5 seconds, t is equal to 5. So we are putting the value of t equal to 5 over here, and it becomes the minus 18.51 ampere. So it is actually flowing in the opposite direction of the current I. So the current after 5 seconds is the difference between the total 50 ampere, that is the steady state current, and the after 5 seconds, that is minus 18.51, that becomes the 31.42 ampere. Let us take another example. Here the switch is kept at position 1 and steady state condition is reached. At t is equal to 0 second, it is moved to the position 2. We need to find out the current in both cases. So at position 1, the steady state current is flowing through it, and the steady state current is 100 divided by the overall resistance, that is 10 plus 20, because these two are in series. So it gives the current 3.33 ampere. And at t is equal to 0 position, the RL circuit starts decaying, and recurrent current is equal to the steady state current e to the power minus 1 by R by L into T. So it becomes 3.33 into e to the power minus 40. So next, let's take an example. In a series RLC circuit is considered here. R, L and C value is given and DC voltage 20 volt is applied. We need to find out the current free. Now for the series RLC circuit, equation voltage equation becomes R d plus L d square I dt square plus I by C equal to 0. And from this equation, we have learned the characteristic equation becomes P square plus R by L into P plus 1 by L equal to 0. And putting the values of RLC given over here, we are getting that P1 and P2 is minus 0.21 and minus 4.79. So the I equation is the C1 e to the power minus 0.21 Pp plus C2 into e to the power minus 4.79 T. Now the current in the inductor and the voltage in the capacitor cannot change instantaneously. So we are considering that at t is equal to 0, b equal to L di dt, or di dt is equal to b divided by L. B is given here 20 and L is 1 Henry. So the rate of change of current is 20 ampere per second. And at t is equal to 0 plus I is also 0. So comparing this, we can find out that C1 e to the power minus 21 into 0, that means as t is equal to 0, it becomes 0. So e to the power 0 minus 0, that becomes 1. So it's actually equal to C1 plus C2. So differentiating this equation at I equal to this one, we are getting that t equal to 0 plus C1 equal to 4.37 and C2 is equal to minus 4.37, because C1 plus C2 becomes 0. So the overall current IT is 4.37 e to the power minus 0.21 C So minus 4.37 into e to the power minus 4.79 t. So in this way, we can find out the solution of series RLRC and RLC circuit with the DC excitation. So these are the references. Thank you.